Hi, everyone. Today is your questions and our answers. This is episode 82 of Get Your Tech On, our show and all things DOCSIS. I'm Brady Volpe, founder of NimbleThis and the Volpe firm. Back with us again is John Downey, senior technical leader at Cisco Systems. John, welcome back. Tell us where you've been.
So 82 episodes. I'm like, I just did the math. That's like 7 years.
Yeah, we've been at this for a while.
If we do one every month. So yeah, it's been over 7 years. Forgot about 2 of the years because of COVID. I just got back from Germany. So it was my first international trip in almost 3 years. I was at the Anga show, however you pronounce it, in Cologne, or pronounced in Deutsch, what is it, Köln, Germany? So it was a good trip. No mask requirements flying over, just mask requirements in trains and stuff. And then we had to get tested before we came back. So luckily I tested negative and I was able to
passed
come
your
back
test.
to Yeah, I passed my test. Had to slip them an extra $50, but I passed my test.
It was worth it. Glad to have you
I'm
back.
like, talk about conspiracy theory. It's like it could be the hospitality industry. It's like, you know what? Hold all the visitors here as long as you can. 2-year quarantine, 2-week quarantine would be good.
Yeah, get some work out of you maybe while you're over there.
Yeah, it'll generate more money for the hospitality industry, hotels and everything.
Yes. So what'd you do when you
But
were there?
overall, it was good. We didn't have a booth there. I don't know if you have the picture I sent you. I don't know if you
Well,
can throw it
actually,
up
I
on the
heard you
screen or
had
not.
kind of a nice booth, kind of a good food booth or something, right? So we can pull up that
Yeah,
picture
people
here.
were loving that booth. Everyone was there flocking during lunchtime.
That's the best booth to have as a food booth because you're bound to get some people coming around and have some nice booth there. So it says Cisco Partners Germany on the side of looks like a food truck there.
Yep.
So you guys actually sponsored a food truck. That's awesome.
we I wouldn't say we sponsored a food truck, but that food truck happened to have our sign on. I'm like, looks like a photo op. So we didn't have a booth there. The European market is very much fiber focused. It's always been fiber focused, and there's cable strewn throughout, but it's PON wherever they can go, which is where US would be going as well if we didn't have so much coax deployed everywhere, right? And we're still milking that cow as long as we can. Yes. And that's why DOCSIS 4.0 is, coming out. That European market is so much more fiber to the home. There is some coax there, like I said, but Cisco decided not to have a booth there this year, and probably because they didn't have a show for 2 years. So it's hard to plan for something that keeps getting canceled or postponed or whatever. But me and Jason Miller went out there to meet some customers, walk around, see what's going on, see some old faces. So it was nice to, what you call, press the flesh, right? Shake actual hands, talk to people in person. So it was good. And the beer is always good too.
It is a different show. I'm hopefully, looking forward to that same show next year, and I'll be back in attendance in full spirit. So, so again, today we're going to be covering questions and answers. Our first question that we have up comes in from one of our listeners on Diplex filters, and he says, "Hi Brady, I work at an internet service provider that is running DOCSIS 3.1 on legacy equipment. Many operators are, but they have 40 megahertz diplex filters," and he says, "We're experiencing issues with upstream SNR variants at 36.8 megahertz. We know it's because of the 40 megahertz diplex filter that are causing issues with the modems that are talking back that close to the cutoff of the filter. My question is, do you know of products that are set up or solutions that may help? I know the best solution is to upgrade to 85 megahertz diplex filters. Unfortunately, those filters are built and not upgradable, or they're built into the amplifiers and not upgradable. We're not ready for a plant upgrade, so we're trying to find a way to make these work without upstream SNR variants. I think they have poor upstream SNR at that high frequency. Thanks in advance for any thoughts or insight you have on this, Timothy P." So they have issues with diplex filters, and I thought, John, maybe we'd just open up and talk a little bit about diplex filters. They're in all of our RF amplifiers, so and we'll tackle that first.
They're not just in amplifiers, right? They could be step attenuators, taps with equalization. It actually has a cutoff.
The fiber node itself that has them, even cable modems
has at least one,
filters.
right? Yep, fiber node has at least one where the RF is, not on the optical side, but on the RF side. So yeah, you have a lot of devices, house amps. You have a lot of devices in the plant that could be contributing to group delay and all these problems with roll off, not just MER, SNR, but group delay, right? Which could be creating low MER, SNR.
Correct.
And it just occurred to me, he mentioned a 3-1 system. So I didn't think about this when you and I were talking earlier, but there's a couple of solutions to that. Could be, if you have a narrow carrier, they usually put the low end. A smaller narrow carrier will have less group delay because it's not as much bandwidth, right? Spectrum. You can put the narrow carrier at the high end, and because the 3.2 is 3 dB higher than a 6.4, you already gained 3 dB more MER. And if you go narrower, you have less group delay in that narrower carrier. Maybe
when
that
you say
would
narrow
work.
carrier, you're referring to like a set-top box return, or
Yes.
these type of
Yes.
carriers that would normally we put at very low frequencies because they punch through the noise.
Yep.
But we're
Maybe
kind of
this is
shifting the
another-
dynamics now and saying, well, just put that at the higher frequency where your diplex
And
filter
maybe it's only
is.
running, and maybe it's only running 16 QAM because
Yes.
it is a set-top box signaling, and you don't really need any throughput from it. You just need it for control traffic.
Correct.
Then I thought he said 3.1. Does that mean he wants to run OFDMA? So the solution to that could be you run OFDMA from wherever you're starting, 24, 27, all the way to 42. But from 40 to 42, you can do an override IUC. So you can say, all right, you know what? Between that frequency, I know it's going to be bad, but I don't want to eliminate it because I can squeeze out a little bit of speed from it. So let's run a 16 QAM just in that 2 megahertz.
Now you call that override. I've also heard that called an exception band, not to be confused with the exclusion band. But exception band is, we'll run say 1024 QAM all the way up to like the higher frequencies you're saying, and then we'll in those higher frequencies where we know we have the diplex filter, roll off, group delay, we'll for the OFDMA channel, the exclusion band, the override band, we're going to run that at a lower modulation, like maybe 256 QAM. Not exclusion, yeah, exception band. 256 QAM, 64 QAM. We can run a very low order modulation in that OFDMA channel, and everyone will be very happy then, because where we don't have the diplex filter, we can run at high order modulations in OFDMA. Where we have the diplex filter using the exception band, or the override? What do you override band? Yeah.
Yeah, and think about it. If you didn't do the override, and just that amount of spectrum was reported low MER, the entire block would be changed modulation just because that little bit of spectrum.
Yeah, all
so you don't want that little bit of spectrum
to
that dictate everything.
Yeah.
So you say, let's do an override. 16 QAM has a really good low MER threshold, so it'll work almost with no problem. And then I can still run higher modulation in the lower band of that OFDMA block.
Yeah. So let me just pull up the slides here again so people understand. Just in case you've not seen diplex filters before, I have a picture on the left-hand side here of some plug-in diplex filters. So as Timothy mentioned, his diplex filters were not replaceable. And that was very common with all the older amplifiers we have. We are making, most of the vendors today are making replaceable diplex filters, which I'm showing 2 here so that you can see the pins that let you plug them in. That's a dime. So that gives you kind of the idea of what the size are. And as John said, normally we have 2 diplex filters in all of our RF amplifiers. You have one on the input and one on the output. And this separates our return from our forward. So on the high side, this amplifies our downstream, and on the low input side, this amplifies our upstream. So our diplex filters are really separating our upstream from our downstream side, and we have what's called a crossover region in here. And this is showing us our, our 40 megahertz or 42 megahertz cutoff for our upstream, and then our 52 or 54 cutoff for our downstream. Depends on exactly where that diplex filter sits. So the challenge that Timothy's running into is he's running a upstream DOCSIS channel very close to this roll-off region, and that's causing poor performance on his SNR as he gets right into this roll-off region on the upstream. And anyone who runs a DOCSIS channel really close to this upstream is going to have problems. And I like what John is suggesting with OFDMA. If we run OFDMA up into this roll-off region here, the lower part of the OFDMA we can run at a pretty high modulation order, and then we can use the as we were discussing, we can drop some of the higher portion, the higher frequency spectrum of the OFDMA subcarriers to a lower modulation. So our low frequency OFDMA will run at a high modulation, and the high frequency, the subcarriers right in this roll-off will run at a lower order modulation if we use that exclusion band, or again, as John called, what did you call it again, John?
Override.
Override
So
band.
exception band or override.
Yep. So, and then visually, what actually causes the low SNR, we can see here. Generally, when you run a DOCSIS channel into that diplex filter band, it's going to cause roll-off, and that's going to cause a problem with the CMTS to actually demodulate that channel, and that's where you get your low SNR. So in addition to the other things that we talked about, if you were to turn on pre-equalization, the cable modem can compensate for that, and this is like one of our classic slides that we always show when we talk about enabling pre-equalization in the CMTS. The cable modem will pre-compensate for that, and then you can end up with a flat spectrum, even in the presence of the cable of the diplex filter. So one of our solutions that we recommend is, so Timothy, if you're not currently running pre-equalization on your CMTS, that would be like the #1 recommendation to do, is to turn on pre-equalization. It can compensate for a lot of roll-off, a lot of group delay issues that you would have by running so close to the diplex filter. That would be the #1 recommendation. The #2 recommendation would be, of course, to move that SC-QAM channel a little lower in frequency to get it away from the diplex filter. And I like John's other suggestions is, if you are in a lower band running your set-top boxes there, you could kind of switch those out with your DOCSIS channels. Move your OFDMA channel up to there. Replace your diplex filters would be another one. And then the long run is ideally get rid of those 40 or 42 megahertz diplex filters and upgrade to an 85 or long-term 204 megahertz return. Other thoughts you have, John?
If you go back a slide, ironically, I remember, I think I provided those pictures long time ago when I started getting the pre-Q, and it turned out what you're seeing there is actually the filter in the modem. I had no diplex filter in my lab.
so then basically what's happening with him, yeah,
in the modem.
Yeah, in the modem itself.
Yes, because the modem has a filter too.
Yep. Yeah. So these pictures have been used over and over and over again.
And if you look at the y-axis, it's like 30 dB of tilt, right? 0 to like -30, or
yeah, that's 10.
Every gradical is like 10 dB, isn't it?
Oh no, that is 40 dB of tilt. So there's 20 dB. Yeah, that's 25 dB of tilt. That's
yeah.
Oh, 30. No, you're right. 30 dB of tilt. That is a lot of tilt. So it is amazing how much the pre-equalizer is able to compensate.
Yeah. And that's just 6.4 megahertz channel width.
Yeah. It's pretty impressive. So those are the main solutions. I mean, you're pretty limited when you're running up against a diplex filter with what you can do. Pre-equalization's probably your best choice unless you're going to start moving channels around. I think that's what you got. Anything else, John?
I mean, another thing people don't realize is diplex filter crossover or rejection area is, the rule of thumb is about 25% rejection area on the highest frequency of your upstream. So 42 megahertz, 25% would be 10 megahertz, 42 to 52. But when you get to 85, 25% of 85 is going to be like at least 20 megahertz.
Yeah.
When we start doing 204, 25%, 1/4 of 200 is 50. So it's a 204, 254 split. So when we start talking about DOCSIS 4.0, extended spectrum DOCSIS, trying to do a 396 upstream, that's 400 megahertz. 1/4 of that is 100. So now you got a 400, 500 split. That's a lot of spectrum you lose to keep the fidelity of that diplex filter proper. So it's just, that's why people were looking at FDX. There is no diplex filter in FDX.
Comes with its own challenges. There's trade-offs with every technology we have.
Of course.
All right, so our next question that comes in is from Renee. Renee says, just want to send a message to show my appreciation of the content you've put up. I'm an escalation field tech, primarily dealing with DOCSIS 3.1 now, and have really broadened and deepened my understanding by listening to your podcast. So thanks, Renee. There are tons of observations I've made over the years that I'm trying to understand. One observation I've seen time and time again is subscriber A with upstream problems that is off the same tap as subscriber B, who has really poor downstream RX or SNR. These types of issues seem to escape bigger detection from the CMTS and are more local. If you have any time to cover this topic or respond and shed light on what the dynamics there, I'd very much appreciate it. So we see this a lot actually in proactive network maintenance, where one subscriber has impairments, particularly in their home, and they're actually impacting another subscriber. And so I drew this on the right-hand side of the map here. And if you're listening to audio, what we're seeing on the map are two subscribers who are showing up red modems. They're impacted either in the downstream or the upstream, and they're off the same mainline tap, off the, different ports of the mainline tap. They show up on the plant map as red modems, when all the other modems around them, are maybe in a green state or a yellow state. And generally, when we troubleshoot these, we find out that it's just one subscriber's home that's severely impacting the other subscriber's home. You go in, we do troubleshoot that. It's normally faulty wiring, a reverse splitter, maybe sometimes I find like someone had a satellite dish installed, and so that satellite dish got connected into their cable plant wiring, and then that will impact the other subscriber's home. And so these are very, very common scenarios, and I'm glad Renee asked the question, because I think it's worth covering a little bit more. And it all comes down into tap port isolation, which we've kind of indicated here. And John, you kind of went a little bit more into depth into this, so I'll let you talk a little bit to this slide.
Yeah,
if you want to.
I call it a port or a spigot. Spigot is like a water spigot, but I mean, some people call them spigots. So those tap ports have port-to-port isolation, but you need to know the internal workings of the tap to understand the numbers. So two spigots or ports side by side might be off the same internal splitter inside that tap. And let's just say, for the sake of argument, that port-to-port isolation is about 20 dB. Now, port-to-port isolation really is dictated by the common port 75 ohm match. It's always based on that. So let's say it's 20 dB. Now, if you go back to that picture and you look at the loss from port A to port D, you'd have to go through one splitter, that's 3.5 dB loss, port-to-port isolation on that primary splitter in the tap, so that's 20 dB, and then another 3.5 dB of loss before you come out the other spigot. So that would be 27 dB of port-to-port isolation from A to D. But from A to B, you only have 20 dB of isolation. So you easily could have problems port to port, depending on how it's internally wired up. And I just thought about this as well. It's going to get worse, I think. We call it adjacent device interference, when we start transmitting higher frequency and higher power. So when we go DOCSIS 3.1, if we go to 204, we're going to have frequencies being transmitted that have never been transmitted before from a house at levels that could be extremely high. So those now, and I know RF is very frequency sensitive, meaning I could have perfect match 75 ohm return loss at 42 megahertz, but what happens if I start transmitting at 85 megahertz? Am I going to have the same return loss? Maybe, maybe not. Maybe I have a kink in the cable, which is more frequency sensitive at 85 or 204. So I think we're going to have some other gremlins pop up when we start implementing 3.1 at higher frequencies and this port-to-port isolation, where the signal bleeds over from one house to another. Yeah, it's really bad in the house itself, and not so bad from house to house. But as you mentioned, it could be house to house.
Yeah, and you bring up an interesting port, because as we look at the slide here, we say that. So on the bottom right-hand side of the slide, and for those of you in audio, talk you through it, we're looking at basically two splitters. We can think of a 4-port tap as having two splitters inside. Ports A and B are off that same splitter, and you talk about the isolation only being 20 dB between them. So that's maybe one subscriber off of port A. That's the subscriber that's having lots of impairments, but he's impacting the subscriber off of port B. That's kind of the challenge there. And as you're talking about DOCSIS 3.1 having more increased noise, we know from lots and lots of empirical data that noise, if you have a lot of noise in the plant, that can impact subscribers upstream. So I think it'll be interesting to see, as you're saying, if say subscriber on port B has a DOCSIS 3.0 modem, as we extend the spectrum, they transmit a lot of noise. Will that impact subscriber on port A? I don't know, but it'll be an interesting use case. Getting back to your Renee's challenge here, and what we see when subscriber A is impacting subscriber B, that's already happening today, where that limited isolation between port A and port B, or the limited isolation between port C and port D, happens all the time, right? We have a subscriber that has lots of noise or lots of impairments in their house, and that's impacting their neighbor. So the way you handle this is you can go out to the tap or to the subscriber's home. You have to clean up the impairments on subscribers B home so they stop impacting subscribers A's home. You get a little bit more isolation, and John, I think you did the math, because you have 3.5 dB more isolation between that tap that splits the two ports. So that gives you, what'd you say, like 27 dB of isolation between port A and port C, or between port A and port D. But it's not a huge amount more isolation, so you still get a little bit more isolation between different taps, right?
No, and another thought was, let's say usually on low value taps, modems are transmitting low power. And if I had at my disposal step attenuators, and you put it on port A, and suppose the modem was only transmitting 35, and you put a 9 dB step attenuator, so now that modem has to transmit 44. So it's still well within its range of power. That extra 9 dB of loss created more port-to-port isolation.
Correct. Or the other way you could do it is you could remove subscriber B, rescan the modem on subscriber A, and see if subscriber A is now healthy, or vice versa, and you can troubleshoot that way. There's different ways you can troubleshoot it, but the subscriber A, subscriber B problem is definitely one that happens out there, where you can't assume that both homes have a problem. But it's port-to-port isolation fundamentally, where this happens all the time, and you just have to you have to find a home that has the actual issue. All right. Question 3 comes to us from Greg T. He says, we've recently expanded our plant to 85 megahertz. Lots of operators doing that. DOCSIS 3.0 modems work without issue, but we have a problem with DOCSIS 2.0 modems having a severely impaired channel just above 42 megahertz. How do we prevent the DOCSIS 2.0 modem from locking onto the 47.2 megahertz channel? Why does it even do this? The DOCSIS 2.0 modem is only spec'd to go to 42 megahertz. And what we show over on the right-hand side here is the DOCSIS 2.0 modem in-channel frequency response. So this is something we get from PNM. It's kind of centered right on 47.2 megahertz, where it shouldn't be. We show the pre-EQ tap response here of the DOCSIS 2.0 modem, and anyone who's familiar with looking at a DOCSIS pre-EQ channel response, so this is the pre-equalizer in a DOCSIS 2 modem, they'll know that this is a completely saturated pre-equalizer in the DOCSIS 2.0 cable modem. So we see a pre-equalizer response in the DOCSIS 2 modems completely saturated. This DOCSIS modem is working very, very hard to stay online, and just not a good scenario. Based on the information from Greg T, we know this modem and probably the subscriber is not experiencing good upstream service, which in turn means they're not experiencing good downstream service. So John, your thoughts, what's happening here?
So we have a saying, if it hurts when you do that, don't do that. So it's like, what's my answer? Don't put a carrier there, So in all seriousness, we know that roll off is 40, 42, somewhere in there. The modem has its own filter as well. And if I'm going to do up to 85 megahertz, and I still want to do single carrier QAM, because there's some 3.0 modems that support 8-channel upstream bonding, just don't put a single carrier QAM right near that region. Move it up to either get rid of it altogether or move it up to like 50 megahertz and above. Because from 50 to 85, you have enough room for 4 channels, 4 ATDMA channels. 4 times 6.4 is like 25.6. So from 50 to 85, you got plenty of room to do 4 ATMA channels. There's no need to put it right at 47 or 44 or 45. Just leave that empty. Make yourself a no man's land right there.
Correct.
And just be done with it. The other option is to get rid of the single carrier QAM, go OFDMA. I mean, why not exploit DOCSIS 3.1 with higher modulation scheme? And then you're probably already deploying 3.1 modems for downstream anyway. So start activating the upstream. Get off the single carrier QAM and go to OFDMA.
Yep. And I think to ask the question, why does this modem even do this to begin with? Because it's only spec'd to go to 42 megahertz, a DOCSIS 2.0 modem.
It's a $20 modem.
Yeah. Well, no, I mean, to be realistic, though, manufacturers have to make sure that the modems perform to the specification, which means if they say, hey, this modem goes to 42 megahertz, they actually have to design the modem to go beyond 42 megahertz in order to meet the specification of 42 megahertz. So, and we've seen this, you and I have both been in development most of our careers, but to design something to go to 42 megahertz, that means you actually have to design it to go well beyond 42 megahertz. So that modem is able to go beyond 42 megahertz, probably maybe even up to 50 megahertz. And so it's able to lock to that 40, I think it was a 47 megahertz channel, is able to lock on it, perform and communicate with the CMTS. The problem is that modem has an internal diplex filter that is at 42 megahertz. So now it's transmitting. If remember, we had another question about modems not performing well when they're locking on that 40 megahertz diplex filter. This is even worse. This modem's transmitting well above its internal 42 megahertz diplex filter. So it's bound to have lots of impairments. It's going to have group delay. It's going to have roll-off, what we saw earlier, probably lots of uncorrectable code word errors, and that's where you have a very unsatisfied modem. If it's a subscriber's modem, it's going to be performing poorly. If it's working in maybe a power supply as a transponder or a set-top box for turning television channels, it's going to be performing really poorly. Then you're going to get bad channel changes, and that's where you run into issues.
And I had another thought, and this is like off the wall. What's masking this and making it work and help it work is pre-EQ. Pre-EQ is helping it work, but you don't want it to work. So maybe you could test where you say, let's just turn off pre-EQ for that channel. Now, pre-EQ will help with group delay and tilt and all that. But in this case, you don't want it to lock on there. But then what happens if you have a modem that does support 85 and you don't have pre-EQ on that channel? Now you're losing the advantage of pre-equalization. Yep. So I was just thinking out loud how I could shut it off, and the 2.0 modems would probably never lock because it'd be so poor.
Well, you can exclude pre-equalization for 2.0 modems if you wanted, right? Based on the OUI.
You can exclude on a per modem basis, but now it's going to exclude it for all the upstreams, and you just wanted to exclude maybe that one channel.
Yes, and that's the other. That's the other challenge that they run into with DOCSIS 2.0 modems, because they're doing load balancing on the upstream. So sometimes these DOCSIS 2.0 modems will lock on lower frequency channels and they'll run perfectly well. Other times, these DOCSIS 2.0 channels, because they're load balancing across, will lock on this higher 47 megahertz channel, and then it's going to perform in an impaired mode. It's going to perform really poorly. So keeping that in mind. So I think when we go to our solution slide here, some of the solutions that we talked about, John, the first one you mentioned, do not run SC QAMs between 42 and 50 megahertz, because that kind of will prevent the cable modem to going up into that extended range where it can still function. It really shouldn't function there, but it can still function, but in a very degraded mode. Then the other one where we talked about is, we're extending our plant to 85 megahertz, not necessarily so we can run SC QAM from 42 to 85 megahertz, but that's where we want to take advantage of placing our OFDMA channel starting at 42 megahertz and running that up to 85 megahertz. And then, John, you talked about cable modem steering, and I think that's something that we've used in the past, but I'll let you elaborate a little bit more on cable modem steering and how that could benefit this solution.
Part of the DOCSIS 2.0 spec is something called DOCSIS low balance groups, and there's one called DOCSIS restricted low balance groups. So you can tag modems based on the type. downstream bonding capability, upstream bonding capability, filter capability. So the modem has to tell us CMTS its capabilities. And you can make a DOCSIS restricted load balance group and tag it for all 2.0 modems and say, all 2.0 modems are relegated to upstream 0, 1, 2, 3. So if a modem locks on upstream 4, it will try to register. And if it's good enough, it will get through. But then the load balance will say, oh, I see that you just came up and you're a 2.0 modem. You're supposed to be on upstream 0, 1, 2, 3. So then it will quickly move to upstream 0, 1, 2, or 3. So you're steering the device to the frequencies you want.
Correct. And I think all of these solutions are going to, can be used to ensure our modems don't run above the diplex filter, above the frequencies we want. We have to be cognizant of DOCSIS 2.0 modems because they're going to be out there for some time. We're going to have them in set-top boxes, power supplies, legacy monitoring, and probably some dedicated customers out there that they're going to hold on to their 2.0 modems, and getting them out of their hands is actually quite difficult sometimes. So
it might be they still have them for EMTAs because they upgraded a 3.1 modem that doesn't have a built-in EMTA.
We still have them for those as well.
Maybe. Who's to say? I thought about this. What exacerbates the issue and makes it worse is if you have modems off low-value taps transmitting 35 normally, they might be able to lock on to 47 megahertz, even though there's an extra 10 dB of loss in that roll-off. The 35 now is 45. Yeah. It has enough range to overcome its internal loss and tilt with pre-equalization to then come back and still work. So one way I could eliminate that is if I use the flexible solution taps that I never allow modems to run at 35 dBmV. I have it designed properly that every modem, no matter where it is in my plant, no matter what type of tap it is, it's at least 45 and above. I like 48 plus or minus 3 dB because I think that's a nice number to be running at.
Yeah, for that modem to be transmitting that high in that 47 dB or above 42 range, it has to have extra transmit power in order to do that. So I agree with you. If all modems are transmitting in that ideal window, 45 dBmV, they're not going to have that power reserve in order to transmit above 42 megahertz, particularly
you could have another modem right off the first tap. It's a 23 dB tap, and the modem's already transmitting 49. So if it tried to lock on 47 megahertz and it had to overcome its internal loss because of the roll-off, and now it had to transmit at 58, it's not going to work. So it's going to fail properly.
Yep.
Because you want it to fail at 47 megahertz because you didn't want it to lock. But the lower value taps, the modems running lower transmit power, have enough reserve to overcome their own internal loss and roll-off.
Indeed. All right. So appreciate it if everyone would hit that notification bell so you get alerts next time we send a podcast live stream out. And if you haven't already subscribed, we greatly appreciate it if you subscribe and hit the thumbs up bell if you like the podcast. Our last question comes in as, why do we call a cable modem haystack a cable modem haystack? And I was sent this image, which really kind of explains the confusion of why we call some of the things what we do in our industry, because this looks nothing at all like a cable modem haystack. So, and John, we'll talk maybe about some of the other things, but this, the answer to the question is there's many types of haystacks out there, and this I think gets into some of the confusion in our industry. So on the left-hand slide here, I have, John, this goes back to your original slide that you took of a true cable modem haystack and what it looks like in the upstream, which is I think you said it was a 6.4 megahertz upstream transmission from a regular SC-QAM cable modem transmission. It kind of looks,
like that's like an FFT, right? Normally on an upstream spectrum analyzer, you see slivers because it is bursty, but we see the entire haystack. It's almost like you did a max hold, right?
Right.
But some test equipment will do an FFT and just paste the whole thing.
Correct. So, but it kind of looks, sort of like I don't know, what's it look like? A haystack. If you look at the two images on the right, these are more, I think, of what as an industry when we think about cable modem haystack, or when we think about haystacks, these are more of the rounded haystacks you may see in a farmer's field, where the hay's been put out for animals to eat in the pasture, rather than the previous haystack, which is a bundle of hay, a bale of hay, or a bale of straw,
I used to
rather.
call it a
These are
Bart Simpson head.
yeah.
Looks like Bart Simpson.
So I think that, is we use, as we were talking earlier, but before we started the live stream, we use so many different terms in our industry that can be really confusing to people. And I think you brought up daisy chain earlier. It's like,
Yeah.
where do we come up with daisy chain?
Yeah. You don't
So
realize the slang and the words we use in the industry until you have to translate them in another language, and they don't translate well. And daisy chaining was one of them, like daisy chaining equipment together, and it translated as flower garment or something. And so it was hard to explain what daisy chaining meant. The other one is piggybacking, and piggybacking is actually in the spec.
yes.
It's kind of funny. We have a slang word that actually made it into the Cable Lab spec. Piggybacking is taking a cable modem bandwidth request and inserting it inside an actual grant, so it's not a contention request. It's going along with real data, which is unicast, which is timed. There's no collisions, but we call it piggybacking because it's hanging on. It's inside. But you think they would have came up with an actual term instead of the English slang term of piggybacking. But it is what it is.
Well, there's many. It's like we have token ring, bucket shaping, all kinds of. We use words that are like everyday words in our language and apply them to technology. I think probably so we can better understand the technology, describe the technology using layman terms, and that's why we probably use like haystack. How do you describe what the shape of a cable modem upstream transmission looks like? Well, it kind of looks like a haystack. But you have to understand what type of haystack we're talking about. So it's really, really important to understand that. So I think these are interesting questions that we get in from our listeners, and it's good to talk about them because it just helps us all understand the industry a little bit better. So those are questions that I had for today. We have more that are out there. Some questions we have in from one for Amin. I hope I'm saying your name right, Amin. Thanks for the kudos there. You just have one question. Why do we see a significant number of correctables on OFDM channels, even though the RxMER is in great range? I think this is a very good question because we've talked about this sometimes in some presentations when we're talking about how in OFDM or in DOCSIS 3.1 we changed the error correction from previous versions of DOCSIS. So DOCSIS 1, DOCSIS 2, DOCSIS 3, the error correction we used was called Reed-Solomon. When we moved to DOCSIS 3.1, and we'll also be using this in DOCSIS 4.0, the type of error correction we're using is called LDPC, or Low Density Parity Check. And Low Density Parity Check is one of the things in DOCSIS 3.1 that has allowed us to use the much more advanced modulation profiles, such as to be able to go beyond QAM 256. So you hear us talking that we're using modulation profiles like QAM 512, QAM 1024, all the way up to QAM 46, and eventually we're even talking about going up to like 16K QAM modulation. So low density parity check gives us the ability to get at least 3 dB better performance than Reed-Solomon error correction. So basically, low density parity check, when we find a bit error in a packet of data, so a packet of data goes from the modem to the CMTS, or CMTS to the modem, and it gets hit by some impairment, and what low density parity check says, oh, I found that error, I'm going to try to correct that error. The same like Reed-Solomon would try to correct that error once, but low density parity check's really aggressive. They'll try to correct the error over, and it's an iterative process. It keeps trying to correct that error until ideally it eventually corrects that. And during that error correction process, it'll generate correctable errors. And so we see many correctable errors from LDPC until we eventually correct that error and ideally don't get any uncorrectable errors. So correctable errors are very common with LDPC and much more so than Reed-Solomon, because it's part of that iterative process of correcting errors. John, I don't know if there's anything you want to add to that to maybe correct me or answer the question in more detail.
So I brought this up, and we should probably do a selfless plug of the presentation we just did Wednesday, right? We both were on a whole day panel, or not panel, but presentation for the Penn Ohio SET chapter. And I'm sure it was recorded and maybe they'll supply it to all SET members. But I know you talked about P&M, pre-equalization, all that stuff. I talked about DOCSIS 3.1, and I brought this up. I said, it's very common to have 100% correctable FEC.
Yep.
A correctable means it's corrected. Back in the old days of single carrier QAM, we knew correctable was going to lead into uncorrectable. It's kind of like inevitable. I could start getting 3, 5, 10% correctable. It's getting worse and worse. Eventually, it's going to get so bad, and MER is getting so bad that it leads to uncorrectable. And that's what we care about, right? Drop packets. Well, with DOCSIS 3.1, the way it does the fast Fourier transform is very complex solution and signal, and how it does time and frequency interleaving, and then this low density parity check. All those things are making this complexity. Like if I have 1 bit in error, it makes it look like the whole block is in error, or it had to fix the whole block.
Right.
So it's a little bit more complex. And I know Ron Rannick did a nice little write-up on this as well, and it gets a little bit too deep in the weeds, but expect 100% correctable. And I tell people with 3.1, don't monitor it. It's not worth it anymore. And most of the test equipment vendors are now taking it out of their thresholds, causing red flags and all this other stuff. Excuse me, worry about uncorrectable FEC, worry about MER and those things. There's multiple things to look at to see that you're getting worse. On the upstream side, it's not quite the same because it's scheduled traffic and all that, but expect much higher correctable FEC on the upstream than a single carrier QAM. It's not going to be 100% like downstream was, but you're definitely going to see a higher percentage of correctable FEC. So you can't really rely on it anymore for an indicator of plant health for DOCSIS 3.1. You can still use it for 2.0 and 3.0, but not for 3.1.
Perfect. Good advice, John. Got another good question here from 905 Cable Guy regarding port-to-port isolation question. What happens when port D and C are open or have cold cut drops attached? I think this is pretty good here because we always recommend. Go ahead, Joe. Wait, you want to take it first?
Philosophically, it's always been, should I terminate taps
or not
terminate taps?
To terminate.
Should I terminate taps and cut the resistor out? Well, then you're not terminating tap. You just put a security cap on there, right?
No good at all.
So
on high value taps, we're going to do a high value to low value, right?
Yeah, high value taps, it's not worth it.
Yes.
It's not worth putting the terminator.
And so,
because
where
the value of the tap is so high, for signal to go out and reflect, it has to go through that tap twice, down and back. And it's not going to interfere with other people.
Although, do you on high value taps, do you consider the neighbor? Because we have port to port isolation, you have one port open. Because if we go back to that concept.
A nature of an open.
You have an unterminated port.
I know. I'm thinking about that because a cable hanging off is worse than an open.
And that's
port.
where I'm going to go with this because
right?
that's the only reason that I would say on a high value tap.
Here it is. Here's my answer. Reflective cavities, and you talk about cavities and reflections and impedance mismatches, right? There's no cavity there.
Until you.
There's no length. There's no length of cable to
Correct.
reflect and come back. There's no cavity. So for the signal to go up and reflect off an open, it's almost back in phase anyway because there's no distance. Whereas if the signal goes through and down a coax and back, you have that reflective cavity that creates the standing wave.
So my argument to you would be, for a technician, where do you tell them, at which value tap do I stop terminating?
14.
14.
14 and below.
14 and below. So terminate everything 14 and below. And then my next question would be, just from a process standpoint, if I have contractors out doing disconnects and they forget to disconnect on a high value tap, they just cut it off because it's much quicker to do that. Now so this gets to 905 Cable Guy's second question. We're leaving stub cables on both high value and low value taps if we're not enforcing terminate everywhere.
That's ridiculous and stupid.
Well, what happens? What's it cause?
And you're creating an antenna.
And
A
that
port by
causes
itself,
standing waves and
looking at the
suckouts.
LRC, inductive, reactive, and capacitance,
Yep.
the way it's created, it won't leak. It's not going to leak. Might leak water.
It won't leak. It won't leak, but it will
won't leak.
cause standing waves and it'll cause suckouts.
Correct. But like I said, if it's a port open, the distance is so close that if there was a standing wave, it would be at like 100 megahertz wide, or maybe 700 megahertz wide.
Likely
there's no distance, there's no cavity. But as soon as you put a wire in there, now you're creating a little antenna. So now you have egress and you have ingress. So some people make the argument that putting a resistor on a high value tap could cause more problems than good. Because if the resistor breaks, now you just opened up the weather seal, and you also create a little wire coming out of there, creating ingress and egress.
I see. So it's I still say terminate everywhere.
Yeah, and you know, that's what it comes down to, is like, well, that's too hard for me to remember which taps. Just terminate everything and be done with it.
Yeah.
And if you have the terminators with the little weather seal, great.
Even better.
If you have terminators without the little O-ring, then that's going to be a problem.
Yeah. Yeah, and I think that goes everywhere for cables and connectors. So None of a Cable Guy also says, oh, we've got French doors to deck. That's a welcome, French doors to deck. We have not seen you before. Is there any reason to have an OFDMA channel hit the CMTS at anything other than 0? I see minus 6 dB receive power at CMTS where I work. And this is something, so John, I think we talked about this before, because I've played around with 0, minus 6, and plus 6 dBmV, and have seen varying results. And my concept here is, do we want the OFDMA channel to drop out before the SC qualms? Do we want the SC qualms to drop out before the OFDMA channel?
The goal of OFDMA is to exploit it to its highest capability, highest modulation, best operation. It has self-healing properties with graceful profile management, so it can change modulation on the fly for individual modems. Why would I want to run at 6 dB lower with 6 dB lower MER?
Correct. Granted,
it is probably 6 dB more robust than a single carrier QAM, but I need that to run 1K QAM. I don't want to run 256 QAM or 64 QAM like a single carrier QAM channel. I want to run as high modulation as I can to get more speed. So the only reason why I would run it lower is I have power level issues, maybe. I have a dynamic range window where my OFDMA was at the high end, and the OFDMA was being told to transmit at 50, and the single carrier QAM at the low frequency was transmitting at 40. That's a 10 dB tilt coming from my modem. If I had to manipulate the CMTS, I could change the OFDMA to say minus 6, which would then make the OFDMA drop 6 dB. And now my DRW is only 4 dB and not 10 dB, my dynamic range window.
Yep.
And that could be a scenario. I'm trying to finagle the CMTS to fool the cable modem's reporting of its dynamic range window. It's a funky game to play, because now you're getting a low MER in that channel.
So trade-offs.
I would go the other direction. I'd be more like, I'm only doing 85 megahertz. A 3.1 modem has easily 5 to 8 dB more power than a 3.0 modem. And I'm only doing 85 megahertz. I'm not having power level issues because the 3.0 modems work. So the 3.1 modem is going to work better. I'm going to tell my OFDMA to be plus 3. Mm-hmm. I'm going to keep my single carrier QAMs at 0, do plus 3 on my OFDMA so I get better MER.
Yeah, and eventually, when most of our modems are DOCSIS 3.1 modems, we'll probably want to have our OFDMA higher than our SC QAMs. Let our SC QAMs drop off first and keep our OFDMA online.
Now here's the kicker. All these upstream channels are going through the same upstream port now. Yep. It's not like the old days where an upstream port was one channel.
Dedicated
now
OFDMA
an upstream port is multiple channels. So you have a gain stage in there that has to do self-calibration on all these different channels. So I know on Cisco side, we recommend, tell people, don't run more than 6 dB delta between channels on the same port, or that self-calibration can get screwy.
Yep. So, hey, I missed a question here that I want to go back and catch. Was I'll get it up here. Dylan, he says, why does that upstream ICFR look like that instead of roll off? And I want to go back to my slides here to answer that. And
I looked at that too, and then I think I figured out what it was.
I missed that. So we're talking about here where we have a lot of group delay. So, and when we have a lot of roll off when we're in a diplex filter. And so this is our in-channel frequency response. We're looking at the output of the cable modem. So the cable modem is compensating for the opposite of what the CMTS is seeing. So if we think about this, the CMTS would be seeing a lot of roll off. It's going to have negative tilt due to the roll off that the diplex filter has. So the cable modem pre-equalizer, what it has to do is compensate for that negative tilt that the CMTS sees. So the pre-equalizer is going to create positive tilt as its output to compensate for the negative tilt that the CMTS was seeing, so that when this signal arrives at the CMTS, it's going to be flat. So anytime, go ahead, John.
I think the confusion is this in-channel frequency response is at the modem, not at the CMTS.
Exactly correct. So we're seeing basically the modem do the inverse of what the CMTS sees. So that basically the CMTS will see a nice flat response here.
Yeah.
And that's basically what's going on. So anytime.
And the way I explain it is like you're pre-equalizing or pre-distorting the modem signal to make up for the plant to hit the CMTS flat. The CMTS wants to see a flat signal. So if we did an in-channel frequency response at the CMTS, it would look flat.
Correct.
But the modem has to transmit this crappy signal to overcome the crappy plant to get a nice flat signal at the CMTS.
Precisely correct.
Is that the technical terms?
It's just like haystacks and piggybacking and crappy signals. These are all technical terms that should be baked right into the specification. So French doors to deck. So he's saying if the OFDMA, and local trees 100, you're on fire. Thank you. So if the OFDMA is at 40 power level and the receiving at the CMTS is at -6, changing it to a receive at 0, you would see the power level at 46. Just making sure I heard that correctly.
Yep.
That's correct. That's exactly how you should interpret that.
And then one other thing is there, and I brought this up during our Web Wednesday SCTE, the difference between the 3.1 modem reporting and 3.0 modem reporting is 3.1 modems reporting 1.6 megahertz equivalent bandwidth. So if you take a 3.0 modem and says it's transmitting at 46 dBmV, you throw a 3.1 modem in there, that same channel, whether it's single carrier QAM or OFDMA, it's going to report, instead of 46, it'll report 40.
Right. So
it will report 6 dB lower. It's still transmitting 46 in a 6.4 bandwidth, but because it reports in 1.6, that's 1/4 of a 6.4. 10 times the log of 1/4 is -6. So that's why you see when you start reporting modem transmit levels, they could be a little funky when you upgrade from the 3.0 modem to 3.1 modem if you don't know what you're looking at.
Yeah, and I think we covered modem transmit levels like a show or two ago. So if you if you didn't catch that one, watch the reruns. Catch us in syndication. Yeah. All right, I think we've covered all the questions and all the incoming questions. So thanks so much in the chat room for the all the good questions you have. And John, thanks for your content today. Everyone, it's been a good episode, and catch us next time. Thanks everyone for watching, and tune in on our next show.
All right, take care.